So why do we believe these bizarre laws? Well, for over 75 years, we've been using them to make predictions for how atoms and particles should behave. And in experiment after experiment, the quantum laws have always been right.
It's the best theory we have.
There are literally billions of pieces of confirming evidence for quantum mechanics.
It has passed so many tests of so many bizarre predictions.
There's no disagreement between quantum mechanics in any experiment that's ever been done.
Not long ago, we thought we had it pretty much figured out. The rules that govern how planets orbit the sun, how a ball arcs through the sky, how ripples move across the surface of a pond. These laws were all spelled out in a series of equations called classical mechanics, and they allowed us to predict the behavior of things with certainty. It all seemed to be making perfect sense. Until about 100 years ago, when scientists were struggling to explain some unusual properties of light. For example, the kind of light that glowed from gases when they were heated in a glass tube. When scientists observed this light through a prism, they saw something they'd never expected.
If you heated up some gas and looked at it through a prism, it formed lines. Not the continuous spectrum that you see projected by a piece of cut glass on your table, but very distinct lines.
It wouldn't give out a smear, kind of complete rainbow of light. It would give out sort of pencil beams of light at very specific colors.
And it was something of a mystery how to understand what was going on.
An explanation for the mysterious lines of color would come from a band of radical scientists who at the beginning of the 20th century were grappling with the fundamental nature of the physical world. And some of the most startling insights came from the mind of Niels Bohr, a physicist who loved to discuss new ideas over ping pong. Bohr was convinced that the solution to the mystery lay at the heart of matter, in the structure of the atom. He thought that atoms resembled tiny solar systems, with even tinier particles called electrons orbiting around a nucleus, much the way the planets orbit around the sun. But Bohr proposed that unlike the solar system, electrons could not move in just any orbit. Instead, only certain orbits were allowed.
And he had a really surprising and completely counter-physical idea, which was that there were definite states, fixed orbits that these electrons could have, and only those orbits.
Bohr said that when an atom was heated, its electrons would become agitated and leap from one fixed orbit to another. Each downward leap would emit energy in the form of light in very specific wavelengths. And that's why atoms produce very specific colors. This is where we get the phrase, quantum leap.
If it weren't for the quantum leap, you would have this smear of color coming out from an atom as it got excited or de-excited. But that's not what we see in the laboratory. You see very sharp reds and very sharp greens. It's the quantum leap that's the origin and the author of that sharp color.
What made the quantum leap so surprising was that the electron goes directly from here to there, seemingly without moving through the space in between. It was as if Mars suddenly popped from its own orbit out to Jupiter. Bohr argued that the quantum leap arises from a fundamental and fundamentally weird property of electrons and atoms, that their energy comes in discrete chunks that cannot be subdivided, specific minimum quantities called quanta. And that's why there are only discrete, specific orbits that electrons can occupy.
An electron had to be here or there and simply nowhere in between. And that's like nothing we experience in everyday life.
Think of your daily life. When you eat food, you think your food is quantized? Do you think that you have to take a certain amount of minimum food? Food is not quantized, but the energy of electrons in an atom are quantized. That is very mysterious, why that is.
So, how could electrons, which are particles, form that pattern? How could a single electron end up in places a wave would go?
Particles are particles, waves are waves. How can a particle be a wave? Unless you give up the idea that it's a particle and think, aha, this thing that I thought was a particle was actually a wave. A wave in an ocean? That's not a particle. The ocean is made out of particles, but the waves in the ocean are not particles. And rocks are not waves. Rocks are rocks. So a rock is an example of a particle, an ocean wave is an example of an ocean wave, and now somebody's telling you a rock is like an ocean wave. What?
Back in the 1920s, when a version of this experiment was first done, scientists struggled to understand this wavy behavior. Some wondered if a single electron, while in motion, might spread out into a wave. And the physicist Erwin Schrödinger came up with an equation that seemed to describe it.
Schrödinger thought that this wave was a description of an extended electron, that somehow an electron got smeared out, and it was no longer a point, but was like a mush.
There was a lot of argument about exactly what this represented.
Finally, a physicist named Max Born came up with a new and revolutionary idea for what the wave equation described. Born said the wave is not a smeared out electron or anything else previously encountered in science. Instead, he declared it's something that's really peculiar, a probability wave. That is, Born argued that the size of the wave at any location predicts the likelihood of the electron being found there.
Where the wave is big, that's not where most of the electron is. That's where the electron is most likely to be.
And that's just very strange, right? So the electron on its own seems to be a jumble of possibilities.
You're not allowed to ask, where is the electron right now? You are allowed to ask, if I look for the electron in this little particular part of space, what is the likelihood I will find it there? I mean, that bugs anyone, anytime.
As weird as it sounds, this new way of describing how particles like electrons move is actually right. When I throw a single electron, I can never predict where it will land. But if I use Schrödinger's equation to find the electron's probability wave, I can predict with great certainty that if I throw enough electrons, then say 33.1% would end up here, 7.9% would end up there, and so on. These kinds of predictions have been confirmed again and again by experiments. And so the equations of quantum mechanics turn out to be amazingly accurate and precise. All the matter in the universe is made of atoms and subatomic particles that are ruled by probability, not certainty.
At base, nature is described by an inherently probabilistic theory. And that is highly counterintuitive and something which many people would find difficulty accepting.
One person who found it difficult was Einstein. Einstein could not believe that the fundamental nature of reality at the deepest level was determined by chance.
And this is what Einstein could not accept. Einstein said, God does not throw dice. He didn't like the idea that we couldn't with certainty say this happens or that happens.
But a lot of other physicists weren't so put off by probability. Because the equations of quantum mechanics gave them the power to predict the behavior of groups of atoms and tiny particles with astounding precision. Before long, that power would lead to some very big inventions. Lasers, transistors, the integrated circuit, the entire field of electronics.
If quantum mechanics suddenly went on strike, every single machine that we have in the US almost would stop functioning.
The equations of quantum mechanics would help engineers design microscopic switches that direct the flow of tiny electrons and control virtually every one of today's computers, digital cameras, and telephones.
All the devices that we live on, diodes, transistors, just to form the basis of information technology, the basis of daily life in all sorts of ways. They work. And why do they work? They work because of quantum mechanics.
I'm tempted to say that without quantum mechanics, we'd be back in the dark ages. I guess more accurately, without quantum mechanics, we'd be back in the 19th century. Steam engines, telegraph signals.
Quantum mechanics is the most successful theory that we physicists have ever discovered. And yet we're still arguing about what it means, what it tells us about the nature of reality.
But in 1935, Einstein thought he'd finally found the Achilles heel of quantum mechanics. Something so strange, so counter to all logical views of the universe, he thought it held the key to proving the theory was incomplete. It's called entanglement.
The most bizarre, the most absurd, the most crazy, the most ridiculous prediction that quantum mechanics makes is entanglement.
Entanglement is a theoretical prediction that comes from the equations of quantum mechanics. Two particles can become entangled if they're close together and their properties become linked. Remarkably, quantum mechanics says that even if you separated those particles, sending them in opposite directions, they could remain entangled, inextricably connected. To understand how profoundly weird this is, consider a property of electrons called spin. Unlike a spinning top, an electron spin, as with other quantum qualities, is generally completely fuzzy and uncertain until the moment you measure it. And when you do, you'll find it's either spinning clockwise or counterclockwise. It's kind of like this wheel. When it stops turning, it will randomly land on either red or blue. Now imagine a second wheel. If these two wheels behave like two entangled electrons, then every time one landed red, the other is guaranteed to land on blue. And vice versa. Now, since the wheels are not connected, that's suspicious enough. But the quantum mechanics embraced by Niels Bohr and his colleagues went even further, predicting that if one of the pair were far away, even on the moon, with no wires or transmitters connecting them, still, if you look at one and find red, the other is sure to be blue. In other words, if you measured a particle here, not only would you affect it, but your measurement would also affect its entangled partner, no matter how distant. For Einstein, that kind of weird long-range connection between spinning wheels or particles was so ludicrous, he called it spooky. Spooky action at a distance.
When you have one particle here and one particle there, and they are separated enough that there is no signal able to allow them to communicate, and they still seem to be talking to each other, then is a big mystery.
What's surprising is that when you make a measurement of one particle, you affect the state of the other particle. You change its state.
There's no forces or pulleys or, telephone wires. There's nothing connecting those things, right? How could my choice to act here have anything to do with what happens over there?
So there's no way they can communicate with each other. So it is completely bizarre. That is the most bizarre thing of quantum mechanics. It is impossible to even comprehend. Don't even ask me why. Don't ask me how it works, because it's an illegal question. All we can say is that is apparently the way the world ticks.